and welcome back. I'd like to quickly cover nucleophilic aromatic substitution and elimination addition reactions to finish this chapter on aromatic reactions. First, let's consider the first reaction, nucleophilic aromatic substitution. Notice that we're not replacing a hydrogen with a different substituent. Now we're replacing a bromine with something else. And in this case, we're replacing a bromine with a hydroxyl group. Now, in order to get this to go, we're going to have a strong electron withdrawing group on the ring, okay, because our ring is actually going to be acting as an electrophile. Kind of similar to an SN2 reaction. We're going to have a halide as a leaving group, and we're going to have a nitro group, either ortho or para, to that halide in order to get this to go. Okay, so we have a nucleophile here. We've seen nucleophiles before, and that's why it's called nucleophilic aromatic substitution. The bromine is going to be a leaving group. So nucleophilic aromatic substitution requires a little bit stronger reaction conditions. We got 70 degrees C. We've got a strong nucleophile. We've got an electron poor ring because we've got that nitro group on the ring. So generally, the only way this is going to go is if we have a really strong electron withdrawing group like a nitro group. You're going to generally see this with an NO2 group, okay? And we also have to have a good leaving group, and the leaving group has to be ortho or para to that nitro group. So let's look at the mechanism here. So the hydroxide is going to attack at the alpha position to the leaving group, similar to an SN2 reaction. Then we get this Meisenheimer complex, which actually has a negative charge in the ring instead of a positive charge. But we have resonance structures that are going to move that negative charge around the ring, so we can move it here. And then if we do that, we have to move this double bond here up to be a lone pair. So this lone pair could also move on around the ring, and we could end up with a negative charge over here at this position. And we could even then move that lone pair down, so we'll have to move that double bond here. We could put that double bond on the nitrogen, okay, and that's going to put a double negative charge on these oxygens. So the nitro group in this resonance structure is actually helping to remove that negative charge from the ring, stabilize that intermediate that's forming in that Meisenheimer complex. That's very important to get this nucleophilic aromatic substitution reaction to work. And notice that this leaving group is para to the nitro group. Notice that negative charge can be either put on the para position or the ortho positions. That's why we have to have our nitro group ortho or para to the leaving group for this reaction to work at all. Otherwise, this reaction will not work. So in our last step, the chloride leaves, and in fact, it's pushed out by this movement of electrons, okay, to give us our product. And that restores aromaticity. So this one, in fact, wouldn't work at all because our bromine is ortho to the nitro group. And notice that in our Meisenheimer complex, we don't have that negative charge stabilized by the nitro group at the meta position. Only at the ortho and para positions is that negative charge stabilized. Okay, so the meta position, if you have the nitro group at the meta position to a potential leaving group, that's not going to work. Now, in the case of sodium hydroxide, when you form phenol, it's actually sufficiently acidic enough to lose a hydrogen, and so our second step then is going to be an acid workup to restore that hydrogen that was on the hydroxide group.